Design of high-rise building by Midas Gen. General contents of this course are: program setting, modeling, boundary setting and vertical loads, lateral loads setting, response spectrum analysis, analysis and result, member design. Midas Gen are general-purpose finite element analysis software. The significant modeling features based on the various element types, material and section database, boundary conditions and load types enable the practicing engineers to undertake virtually all types of structural analyses. However, some restrictions apply to the features in that some of the features cannot be used simultaneously. For example, support settlement analysis and heat of hydration analysis cannot be performed simultaneously. First of all, we take a look at program setting. Start a new model by press Ctrl+N. Setting units for program is always the first step. Many errors and mistakes can be avoided by using consistent units through projects. The coordinate system can be set in UCS/GCS tab. The coordinate system defines the orientation of structure members and forces. Default setting can be used if there is no special requirement. Change view direction will automatically change the viewpoint to view the model from the Z direction. Structure can be analyzed three-dimensionally or planarly. Those options can be selected in structure type. (2D) analyses can be used in some buildings where lateral loads, such as wind load, mainly act on one direction. However, high-rise buildings must be analyzed three-dimensionally, 3D. Lumpur masses option converts the total mass of an element from distributed to the nodal points of an element in dynamic analysis. Users can convert self-weight into Lumpur mass in 3 dimensions, x, y, z. Lateral direction, x and y directions. Vertical direction, z direction. Under seismic actions, vertical movements of building are usually small and can be neglected because of 2 reasons. First reason is enormous self-weight. Second reason is vertical response spectra of ground are often small. Therefore lateral behavior is more important in most cases, so converting to x, y can be used to save time and computation effort. Align the tops of line elements in the xy plane such that their top elevations line up at the floor level. Without beam's top alignment, beam elements are aligned by centroid axis, so floor surface is not flat. With beam's top alignment, beam elements are aligned by top surface, so floor surface is flat. Align the tops of plate elements in the xy plane such that their top elevations line up at the floor level. Without plate top alignment, plate elements are aligned by centroid axis, so floor surface is not flat. With plate top alignment, plate elements are aligned by top surface, so floor surface is flat. After set up everything, let's start modeling the building. A simple structure is modeled to illustrate the process. First of all, we need to define all element properties. Element properties include material properties and section dimensions. Materials can be defined in Material, click, Model Properties Material. Click Add to add new material property or Modify to modify available material properties. Select Concrete for reinforced concrete design. Material properties according to variety of design codes, ASTM, JIS, KS, etc., can be selected from Midas database. Select Concrete C24 from Korea Industrial Standards, KS01. Sections of columns and beams can be defined in Section, click, Model Properties section. Select Solid Rectangle for Concrete section. Select User to define section dimensions, or select DB to use sections from Midas database. Define section depth, h, and section width, b. Select thickness to define wall thickness. Select Add to add new thickness property. Input the wall thickness. Press Alt+1 to open Tree menu. Tree menu is used to model all types of elements. The locations of all elements are defined by nodes. Use Node tab in Tree menu to create nodes. Elements nodes can be extracted from structure plan. They are the ending and intercepting points of elements. Click Top to set plan view. Select Create Nodes to draw new nodes. A node is defined by 3 coordinate values. For example, This node has 3 coordinate, x, y, z, equals 0, 6000, 4000. Coordinates are separated by comma. Translate node tool can be used to save time when duplicate nodes. To duplicate nodes. First of all, click to select single to turn on selection mode. Hold left mouse cursor and drag to select all nodes that we want to copy. A selected node is highlighted by magenta color. Select Copy to duplicate nodes. Select Copy Direction. For example, if X direction is selected, then new nodes will align with original nodes in X-axis. Input the copy distance and number of copied nodes. For example, 3 at 6000 is copying 3 times with equal distance of 6000 mm. Users can also input different distances between nodes and separate those distances by commas. For instance, 6000, 5000, 4000. Click Apply. Click Fit to show all the nodes in the view direction. Now we have 4 nodes, 1 original node and 3 copied nodes. Repeat the process for 4 nodes to duplicate nodes along y-axis. Now we have all required nodes. Use Element tab to model columns, beams, and walls. Use Extrude element to model columns from nodes. Select Node to Line element to model columns from nodes. Select Column Material. Select Column Section. Beta angle defines column's orientation. 0 degree, 90 degree, 180 degree. Input extrude distances according to directions, x, y, z directions. In here, -4000 mean that our columns will be expanded 4000 mm below the selected nodes. Select 12 boundary nodes to create boundary columns. Click Apply. We have 12 columns. Click ISO for 3D view. Retune to Plan View and select Create Element to draw beam. Select Beam Material and Section Properties. Draw beam element by left-click to 2 end nodes of the beam. To modeling wall, we first draw beams at wall locations. Retune to Extrude Element tab to create wall. Select Line Element to Planar Element. Select Wall in Element Type. Select Wall Material and Thickness Properties. Select Membrane to calculate wall with in-plane and vertical strength, neglecting out-plane strength. Input extrude distances according to directions, X, Y, Z directions. Select temporary beams at wall locations. Click Apply. Click ISO for 3D view. A one-story structure is finished. Now, let's try a much complicated structure. A real-time instruction will be used for demonstration. We will create a L-shaped building with 3 types of column and 2 types of beam. First of all, it is program setting and defining element properties. Secondly, we create nodes. After creating nodes, we extrude columns. Elements can be modified. After finish all columns, we can draw beams. Users can use translate element to duplicate identical elements. This is the end of today's lecture. Next class, we will learn how to model a multi-stories building.